adopted some kind of crude alphabetical scheme for the initial listing. And I think that is indeed you. You should go ahead.
All right, so I'm going to start with a quick 4-minute run through of a selected set of Leonard's slides, just to remind you what we are interested in. And what we're interested in is verifying full functional correctness properties at the highest level of interesting C programs, both sequential and concurrent. So, you know, the verified software tool chain is meant to be an expressive separation logic, implemented and proved sound with respect to an actual semantics for C, enabling semi-automated, you know, interactive proofs in to construct functional correctness proofs that connect to model level reason. And, you know, so we have papers about the core foundational semantics and about the proof automation system. We have a workflow in which you compile your program and then do interactive proof. And we have been able to prove some non-trivial application programs correct to really non-trivial specifications in memory management, generational garbage collection, 2 or 3 cryptographic primitives, networking, communications, and so on. And so, for example, in our HMAC DRBG proof, we're able to prove that some C programs from the open source libraries such as Embed TLS and OpenSSL actually implement the functional models specified by the National Institute of Standards, even though the C programs do all sorts of abusive but not illegal things to their data structures. And we find that the more abusive a C program is in a legal way, the more work it takes to verify that program in VST. The proof automation, flies pretty well on ordinary C code, and the more you do clever things with your data structures, the more interactive work there is to do. But then we also are able to prove that the functional model has the right high-level properties. And that's because the functional model is just a relation in Coq or a function in Coq that has nothing to do with C programs, and we're able to use domain-specific mathematics to prove things about functions in Coq. But that leads to a very important point, that the specification language for VST is separation logic, in which the contents of memory is related to arbitrary Coq mathematical structures. That Coq is part of the specification language of this C program verifier. And that is what enables us to connect the low-level proof that the C program correctly implements some functional model to the high-level proof about what the functional model accomplishes for you. So we've done that also for a little web server example. We've done it for a generational garbage collector, where the sort of mathematical structure of the functional model is directed graphs. And we've done it for a malloc-free system, in which, in this case, the functional model is fairly shallow related to the properties the user really wants in separation. In our proof about forward erasure correction, which you can see next week presented at CAV, the C program did too many clever things with matrix representations that, we can represent all of them in separation logic. And then at the higher level, it did too many clever things with linear algebra and finite fields that we were able to use the mathematical components library to represent. So once again, critically important that functional models that we verify in the C verifier are expressed in Coq so that we can seamlessly connect the high-level properties proof that has nothing to do with C code to the low-level thing. And now VST can also do concurrency in 3 different styles: the old-fashioned lock invariants and daring semaphores, which works quite well for some applications. And then on top of this, we also have iris style expressive invariance for atomic operations with ghost states that also incorporates the Tada style of logically atomic specifications. And for those latter two style of concurrency reasoning, William Mansky is the main person responsible for implementing these in VST. And finally, we can do modular verification of modular programs in C. If we view a .c file as implementing an API, and the .c file uses abstract data types, that is private data representations that are not meant to be used by the clients of the API, we can express this modularly in VST, in effect using Cox existential quantification as the encapsulation mechanism. And this is the verified software units system designed by Leonard Beringer in the last few years. So I think it's also important for C program verifier benchmarks to be able to test whether you can do modular encapsulation in your verification of the modular programs that you have in the C code. All right, so now let me switch to some slides I put together yesterday. And again, the reason we're all here today is because we're interested in C program correctness verifiers. And it's the correctness word that's really the difference between this and the SVComp competition. That those tools scale very well with a higher degree of automation than we can currently achieve, because they are proving only those properties of the program that you can manage to scale with automation. And many of us are interested in full functional correctness, and that doesn't scale as well without a lot of user interaction. So when Peter was saying earlier, we're not scaling in that style because we can't, this is the essential reason that we can't. And it's okay that we can't. If we want full functional correctness verification and the year is only 2022, then we're not going to achieve full automation. We must necessarily have interactive uses of the tool. That requires people to learn the tools, and that slows down the sort of scale of what we can achieve. So here are my desiderata for what C program verifiers should be able to do and what the benchmark should test. That they should be multi-level. You prove not only that the C program implements some portion of a functional model, but you can connect this to a mathematical proof about your functional model in whatever application. So for VST, that means we can have conc in the middle. There may be other approaches. And the proof system for C program proofs should be expressive enough to verify the all too clever things that real programs do in C, with passing portions of data structures from one place to another and so on. And the ability to use whatever mathematics you need in the application domain is achieved by using a specification language that's embedded in a general purpose higher order logic proof assistant, but there may be other ways to achieve that. I mentioned modular verification of modular programs with sealed data abstractions. Of course, all of the benchmarks we're doing should be, open source. I think it's sometimes useful to take benchmark programs from the real world, but we should take open source programs. And finally, if the benchmark is at all non-trivial, then it should be documented in a paper somewhere that explains, what's the point of this program? What are the interesting properties we're going to verify? And what are the invariants? If I'm going to use somebody else's tool to compare against mine, certainly I want to cheat by knowing what all the loop invariants are and the preconditions and the postconditions. There's no need for anybody to rederive that. So documentation of what the invariants are in each benchmark program is not cheating. It should be done as part of the benchmark. And finally, as we know, C programs are not necessarily portable. Some C programs will work well in 32-bit mode, and others will work well in 64-bit mode, and some will work well in both. And in VST, you can prove it in either mode, and some of our proof scripts work the same in both, but at least each benchmark should be documented. With regard to Peter's list of C program features, I tried to write them all down here. In bold are the ones that VST supports. crossed out are the ones that VST doesn't support. And in regular font are the ones that either I didn't understand what he meant or VST partially supports. But, you know, Peter expressed this as benchmarks for systems code verification. I don't think we should limit ourselves to systems code. Systems code is important, but applications code is also important. And I am just as interested in applications as I am in systems code. And yes, we should support concurrency. Zhang said C does not support a reasonable concurrency model. That's not true. C supports more than one, more than 3 reasonable concurrency models. It is possible to write concurrent programs in C and even to prove them correct. And Zhang has done it, and I've done it, and others here have done it. It should be worth having some concurrent verifications. So the stuff that Frank Vidic put together a couple of years ago is inspirational as a start for C program verifiers, but I don't think it exercises all of the desiderata that I listed before. It's big on small programs that hit a lot of the features of C, but it doesn't, to me, emphasize the whole issue of the richness of the specification language for really expressing full functional correctness. It's not exactly wrong in those senses, and the benchmarks are fun to do. As you can see, I've got about half the points in the first summer after the thing was announced. And then I got tired of it. And as you can also see, Bart got tired of it a lot sooner than I did. But these are not bad benchmarks. So last week or 2 weeks ago, I put together a little catalog of open source program examples that we have verified and documented in the verified software toolchain. And you can find it in the VST GitHub in the catalog of examples. And they're almost all multi-level unified, composable, low expressive, high expressive, modular, open source, documented, and 32 and or 64-bit. Here they are. Most of these programs are not too long, but they're not tiny either. And they have non-trivial stuff going on, both at the low level in the C program, how the data structure would represent the functional model, and in the high level of why the functional model works. They exercise, nowadays, floating point, for example. All sorts of things are exercised here. I would add, if I were doing it this week instead of 2 weeks ago, I would add one more concurrent example of sort of parallel dot product using pretty ordinary semaphores, no fancy atomic locks. But these are all out there, and the community could review the C code and see if these are the kinds of things we want to use as verification examples. And with that, I will stop.
Right, thank you. You are to time. Have extra points. If only we were doing points.
Points if I'm going to get points.
Yeah, well, maybe so. We don't have some hope of regaining the schedule. Maybe we should only have a few minutes of discussion right now. Let me ask a question. So the thing that slightly scares me about picking these or even some of these big examples is they would just be too big. Right? It would be too major an exercise for all the systems to do them.
Maybe, one thing I find when I'm actually doing a verification is I keep going back and forth because I haven't gotten the invariants right. So you get to the place where the invariant fails and you go back up and change the thing and you go back and forth. And this is true either in VST or in Daphne or in Verifast or in any of these tools. But what if the benchmarks came with fully accurate invariants that you just have to type into your own verifier, right? Because, any of these verifications that somebody has done in Verifast or in VST or whatever, you'll be able to rely on the invariants. And even though the tools are difficult to learn how to use, sometimes reading the invariance is much easier in somebody else's tool than actually learning all of the interactive stuff you have to do.
Yeah. Robert remarks correctly, you might want, depending on the system, you might need to tweak the invariance, but certainly it would help. Let me ask a different kind of question. So suppose in the dimension of explaining how these things work, so you might like to muse, and everybody else might like to muse, what would be good examples that would be small enough that one could explain, the essential things that each tool was doing commonly for the same examples? And for that, I think all of these would be too big. One would want something much smaller.
One thing I would suggest is there are 2 or 3 good explained examples in Software Foundations Volume 5, which is the sort of tutorial introduction to VST with exercises. And so the 3 kinds of examples, there are some little string library functions. Those are not so interesting. Second, there's a hash table with external chaining, a very classic data structure that, not a long program, and everybody understands what it's supposed to do, and you'll be able to read the spec. And third, there is a worked example demonstrating the verified software units idea of modular verification of modular programs. So tiny little programs that are factored into tiny little modules just to demonstrate modularity and with full explanation. So I would propose that one. That's one place you could find some explain examples tuned to be small. They're meant as small enough to be a tutorial, but small enough to be a benchmark is about the same thing.
Yeah. Any other quick questions for Andrew? Or points come up? Shall we continue?
I think you should just talk.
Rick has his hand up.
Sorry.
Okay. So with these examples, being the second one to do them is paying much less than being the first one. If you're the first one, you can write a paper about it and publish it. It's like, look, we have verified this nice cryptographic primitive or anything. If you have a Me Too paper, like, look, I can do this too, who will be interested? All the referees will say this has been done already. So that means that doing these smaller examples, I think, will be better, because then people just do it for fun and not so much they don't need to spend all that work for something that will be a Me Too paper, I think. So that was my thought.
One can also imagine, I don't know if we would do this, but one can imagine writing a paper with an enormously large number of authors that presents the comparison somewhere down the road. That might be too long to fit into a conventional paper, but it would be good to have it exist.
Yes, that is true. So long ago I had this square root of 2 booklets, which is the irrationality of square root of 2 in many proof systems, 17, I think. So yeah. That sounds a bit like what you're describing, but that was just one very, very small theorem. So if you do a full benchmark that style, I don't know.
Yeah.
But